Now, let us discuss one example to explain the cram's rule. So, we have already discussed the cram's rule. So, according to the cram's rule, the nucleophilic addition is taking place in a carbonyl group which is already have a chiral center. Then, we know that the carbonyl group is sp2 hybridized and it is a planar structure. So, there is two possibility for attacking the nucleophile on the carbonyl carbon atom. One is in the upward direction and the second one is the downward direction. So, according to the Cram's rule, we should arrange the substituent which is attached to the chiral carbon atom which is already present in the starting material. I have shown the chiral center as asterisk sign, and we have to arrange the substituent which is connected to this chiral carbon atom as medium, small and large according to the Cram's rule. And then we have to represent our starting material in Newman projection formula. Then we should do the nucleophilic addition in the carbonyl carbon, and the attack must be in the angle of the 109 degree. Okay, then due to this addition we will get a new chiral center, and in this reaction a new chiral center is generated. So that's why it is known as 1:2 asymmetric induction, because we have to assign the first chiral center in the starting material as 1 and the newly generated chiral center as the 2. So that's why since we are inducing an chiral center in this reaction, that's why it is known as 1:2 asymmetric induction. These are the main points of the Cram's rule. Now we will discuss one example. So consider this example. First example I have shown in the top of the slide. So this is the chiral carbonyl group which is attached to a chiral center, and the chiral center I have shown by the asterisk sign, and this chiral carbon atom is attached to the 4 different substituent. One substituent is the COCH3 itself, the other one is the CH3, and the next one is the pH, and the last one is the hydrogen. Since the attack is taking place in the carbonyl group, we have to leave that group, COCH3 group and COCH3 group, and we have to assign the remaining substituent as small, medium, large. So while we comparing the hydrogen, CH3 and pH, the hydrogen is the smallest group. So we have to assign the hydrogen as S. And then there are remaining group is the pH and CH3. So we have to assign the M for the CH3 and the L for the pH. Now, so if you are assigning the small, medium, large, our starting material is just like this. Hydrogen is represented as S and methyl group is represented as M and pH is represented as L. We know that every optically active compound or every chiral center has an configuration. So we have to find out the configuration of this chiral carbon. We have to give the first priority to COCH3 group. So assign the COCH3 group as 1 and pH as the 2 and the CH3 as the 3. Since the order of the rotation 1 to 2 to 3 is in the clockwise direction, so that's why this chiral carbon atom which is already present in the starting material has an R configuration. Now we have to apply the Cram's rule. So for applying the Cram's rule, first of all we have to study the structure of the carbonyl group. So carbonyl group, as we know that it is an sp2 hybridized carbon atom. So it is a planar structure just like that. So the nucleophile, here the nucleophile is the lithium aluminum hydride. And we know that the lithium aluminum hydride is used for the reduction, and the structure of the lithium aluminum hydride is just like that. Lithium is existing plus, and AlH4 is a negatively charged, and the attack is taking place. The actual nucleophile is the H minus ion. H minus is the nucleophile. So the nucleophile can attack the carbonyl group from the both sides on the top or the bottom. So in order to represent the nucleophilic addition of the nucleophile, we have to represent our starting material in the Newman projection formula. While we are writing the Newman projection formula, we have to always keep in mind that the carbonyl group which is attached to the two substituent, one is methyl group, the other one is the chiral center. So always represent that chiral center on the away from the observer. Okay, and we are observing the molecule along the carbonyl group, so we should write the carbonyl group as the front carbon, and because we have to induce the chirality in that carbon atom, so we should always write the Newman projection formula according to the view from the along the side of the carbonyl group. So while we are observing the molecule along the side of the carbonyl group, the CH3 group is 180 angle apart from the carbonyl group. So we should write the Newman projection formula just like that. The CH3 which is 180 angle apart from the carbonyl group, and we have to arrange the backside carbon atom, that is the chiral carbon atom which is already present in the starting material and away from the observer, and we have to assign the small, medium, large according to our earlier Cram's rule prediction. And then we are doing the nucleophilic addition. So here the hydrogen is the nucleophile, and the nucleophile is attacking the carbonyl group in the angle of the 109. So the product, there is a newly generated chiral center is produced, and this is the final product. So while we are closely observing the final product, we can see that we have to assign the starting material, the chiral center which is already present in the starting material, as 1, and the newly generated chiral center is the 2. Since we are introducing a new chiral center, that's why this type of the induction is known as 1-2 asymmetric induction. And we know that if you are doing the nucleophilic addition, there are two possibilities, and I have shown these two possibilities here. But the configuration, the difference in configuration of these two products is that already existing chiral carbon atom. So the configuration of the already existing chiral carbon atom remains the same. In this example, the configuration is R. Now there is a new chiral center is generated. The configuration of the newly generated chiral center may be R or S. That we cannot. That will depend upon the example or the starting material. Okay. But according to the Cram's rule, we are expecting the two products, that is R S or R R. So in this configuration, there is only one difference. Either it may be RR or it is RS. So the configuration of the one of the chiral center is fixed, and we are changing the configuration of the other. That's why this center is known as diastereomeric phase. We are already studied the diastereomeric phase in the last chapter, that is in the stereochemistry. So this is an example for the diastereomeric phase, and since the product is a diastereomer, the product produced is a diastereomeric compound. So I hope that you understood the Cram's rule and the nucleophilic addition on a carbonyl compound. I am discussing the next example, which is shown by the bottom of the slide. PHCH3HCHO. This is an aldehyde, and there is a chiral center is present in the aldehyde group, and we have to arrange the substituent of the chiral carbon at small, medium, large. Here the small is again the hydrogen atom, medium is the CH3, and the large group is the pH. And according to the Cram's rule, we have to represent this molecule in the Newman projection formula, which I have shown. And the nucleophile is the methyl group, And for addition, for adding the methyl group in the angle of the 109 degree to the carbonyl group, and the product is an again the new generated a new chiral center is generated. That's why it is an 1:2 asymmetric induction. And since the product is a diastereomer, so this attacking site is also diastereomeric phase. So Cram's rule is very important, usually asked university question. So this is an application type of the rule. So they will give an starting material, and we have to predict the product. That is the way of university question. So one of the university question is the state and explain the Cram's rule, or they will ask the application type questions. Hope that you understood the concept. Thank you.